Yeah, I used to be good enough to be setting up and ready right when the minute hit. And as soon as it was exactly the second I was supposed to be talking, I would start talking to not waste a single second. Those were the days back when I had that kind of time and ability and wasn't doing it. Anyway. So last time we were talking about Turing machines. Should probably start with some announcements though, because we actually have an exam on Friday. So exam on Friday. You can get this week's homework in before Wednesday. You can get feedback on it. So I will have office hours after my next class from 11 to 12. Anything else? I think that's about it. Again, this is a very easy class to have announcements for. Is there an exam? Is there a homework? There's a project due in, what, a week and a half now, something like that? November 7th. Yep. So get started with that, and I'm happy to help you get started if you are struggling to get started. Last time we had our first example Turing machine program of just 0, 0 *, and now I have actually fixed that as of what, 2 or 3 minutes ago. So it's a 3-state transition, not the 2 that was on the board, and here are the 3-state transitions that will get it done. So we're going to start today with another example. So hopefully you were living, breathing, and dreaming Turing machines over the weekend. We're going to hop right back into it with another example. We're going to go with a context-free language. We showed that A to the N, B to the N was not regular, but was context-free. So we could have an NPDA for this. The question now is, can you design an equivalent Turing machine? And the way you're going to go about this, using hints as you get started, is that you can imagine that the A to the N, B to the N is already on the tape. I recommend starting in English. Think about how you might write a program to, if this was just a string and you had the ability to move left and right, how would you, if you could dictate multiple Turing machine moves at once, how could you specify how you would accept this string? You can come up with an English pseudo Turing machine code-ish solution, then you can break them down into what would be similar to methods or instruction sets. You can see some complexities with this. There's kind of again, a moment of brilliance that's needed with this that may not be readily apparent.
I feel like it's fairly straightforward. Like, you just, on the tape, you read an input, you put in a character and you just shift over it. And then you keep doing that until you run out of A's. And then once you're out of A's and you start doing B's, then you read over the same tape again. and then see if they match.
How do you differentiate A's that you've seen from A's that you haven't seen? Or A's that you've mapped to a B and A's that you haven't mapped to?
Well, if you're looking at the strip of the tape, right?
Yes,
So as you go through the tape, you're going through the number of A's. And then as soon as you see a B, because of this format of it, then you just start counting backwards. If you find it earlier before there's more continuous tape, like the next character is not empty, then obviously it fails. You have more A's than B's. If you hit an empty character before you finish the B's, then you have more B's than you have A's. At least that's the only thing that I'm going for. I'm using it like it's a stack, basically.
yeah,
Would, does this imply that it has to be in the form A followed by B?
yes, all of the A's must be before all of the B's. So we have, thinking of it like a stack is good in that you can. Although to do that, you have to be able to count them or store them somehow.
Mhm.
So let's say we have 10 A's in a row, except that how do you know that there were 10 A's? There's no way to know or count them easily.
Mhm.
So we go see the first B, we say, great, how do we map this to an A? Is there some way to associate that with some A that we've seen before, or do we go all the way to the end of the B's and then try to do something with the bookends of the ends of the A's and the ends of the B's as you go back and forth, trying to map them that way? There's no easy way to just count like we could in an NPDA. Just throw something on a stack, throw something on a stack, throw something on a stack. However large the stack is as many of them as we've seen before. Not quite as easy a way to do that this time. Do remember that you're free to modify what's on the tape if that helps you. There are ways to do that and not do that in ways that would be helpful. Basically, there's a solution where you modify what's on the tape. There's a solution where you don't modify what's on the tape. There are runtime concerns between those two ideas, though. Do note that what's on the tape when you're done does not have to be A to the N, B to the N. It can be something completely different. The goal is just to accept or reject.
Can you modify the tape by just taking all these and putting next to all the A's? Is that the way, you can properly modify the tape?
Interesting. So how would you design a program that does that? So you're going to have A, B, A, B, A, B, A, B at the end of that somehow. You have to specify how that is done without allowing yourself to override any of the characters. Right.
What do you mean tell others to write to get characters?
So you have a bunch of B's. If you want to go backwards and put that B in the second A's position, you'd be overriding an A. So now you have two more B's than you have A's if they were equal before. So let's say you had something like A, B, B. You go to the first B, you go replace the second A, you'd have A, B, B, B at the end now. But you would be in a state where you know that you had overwritten an A, so you need to go do something about that, kind of propagate it backwards. That could work.
But it is within the rules to be able to say like, now this B doesn't exist here anymore, now it's over here.
Yep.
That's okay?
You have full, total creative control over what's on the tape in any way that you can answer that question. It's just that you have to perfectly map the input to the right output decision. And you can't assume what's on the tape is of the form A to the N, B to the N. If it's not, though, you want to reject.
Does the Turing machine know where the middle of the tape would be?
Nope. Not unless you have some way of specifying that. You could create some kind of tape character that you then go find it. Something like, if this is in the form a bunch of A's followed by a bunch of B's, you could go make a mark as the first B, move all the way to the end, write an extra B at the first blank. And now you have put a marker between the A's and the B's. You could do that.
Yeah, route I was thinking earlier.
Yeah.
Essentially, you'd have. This is like really work intensive, but like, it would be, you make an array that will be the entire string's length, right?
Mhm.
Then you then you do a for loop, tons of stuff, wasted, I feel like there's a better way to do this, but you could just. As soon as there's not an A anymore, you make a new array, As soon as there's not any A's anymore, you stop adding A's to that array. And then you create another array of B's, and then you start with the B where that last one extended, add them all the way up to the end of the string. And then you do another loop where every single time you add an A, and then from the A array, and you have a B from the B array, and can't go higher than either one of their lengths. And you keep doing that, and every single time, and then you iterate through it again, and you check if there's ever an A after an A or a B after it.
Interesting. Even saying something like, and then you go through a loop, that's going to be a challenge with regards to specifying it on a Turing machine tape.
Yeah.
I agree with you that that is very algorithmically intense for a Turing machine. I think it might work. That said, there are simpler methods. In fact, I wouldn't give this to you if the answer was do something that would take an hour on an exam. There is an answer to this that such that I would be okay throwing it on an exam. And it would take maybe at most 5 minutes, I would think, to come up with the associated Turing machine transitions. So think, how can you make this simpler? How can you determine yes or no to this string in a reasonable amount of time? The best solution for time requires the use of additional stack symbols, not stack symbols, tape symbols. The less efficient one, you can just use the A's and B's that are already there and just specify some transitions that figure it out. The extra tape symbols that I was referring to involve whether or not the character has been seen or not. Or has been mapped to an associate. If it's an A, mapped to an associated B. If it's a B, mapped to an associated A. If we do this, what should we do next? If we have seen an A, what makes sense? How do we specify? What do we want to do with that? Seen A.
I guess we could iterate until we enter the string or the part of the string where the B's are, and then check off a B.
Yep.
And then go back and forth between the two of them.
That is exactly what we're gonna do. So we want to move the read write head right. And as long as we see A's, we continue to move right. As soon as we see our first B, then we're going to change that B into a Y. A seen B. So now we've mapped an A to a B, and on the string, on the tape, now we have an X and a Y where that was. Every other A is still an A. Every other B is still a B. But that single leftmost A and that single leftmost B have been replaced with an X and a Y. Then we move all the way left until we see that leftmost A. We know to stop when we find the X. So basically, we're gonna move left until we see an X, then move right and look at and make sure that what we're at is still an A. So at the end of that process, the read write head would be back on the new leftmost A. And we could repeat that process. A's into X's, B's into Y's, A's into X's, B's into Y's. If the string didn't adhere to that form, there would be something that we didn't expect here, which would be okay, we would just fail immediately. So if we've seen an A and there isn't an associated B, we wouldn't have a transition defined for that, so we would fail, which would say that there were more A's than B's. Yeah,
And that's the more efficient answer.
this is the more efficient in terms of time answer, yes.
Seems like there's so much to reverse.
Yeah, when I asked about the middle, that's kind of what I was
Yeah.
thinking of doing.
Yeah, it's just that's even still, there's no easy way to determine how many A's are there. So on one pass, you can't count them easily.
Only we had O of 1 time complexity to search any part of the set at one point.
Well, a lot of things that are assumed to be O of 1 aren't actually necessarily O of 1, depending on the hardware.
That's fair.
There is one check that needs to be done at the very end of this, which is if we've mapped the last A to a B. So we have something like B, and we've gone all the way through and marked X, Y, X, Y, X, Y. When we go back and we see that when we move to the X, move right, and we see a Y instead of an A. That tells us that we're done with the A's. We still have to go verify at the far right hand of the string that there's nothing out past that last Y. Because otherwise then we would accept B. Or something of the sort. So with all of this knowledge, try to write this program. I think there's something to be said about now if you try to fully understand this and map it, that there's a lot of complexity to even something that seems fairly simple. The other way to do it would be to have a leftmost A and map it with the rightmost B, and then move inward and meet in the middle. But the amount of rights and lefts is double in this case. We don't map the leftmost, the leftmost, the leftmost, the leftmost, the leftmost, the leftmost, etc. We're mapping the leftmost to the rightmost as we move inward. Actually ends up being the same. So yeah, it doesn't really matter which way you do it. I'll do leftmost to leftmost. But leftmost to rightmost is fine. But my recommendation for people is break the associated transitions down into groups. This is very similar to making methods when you write programs, just for organization purposes. Here would be the methods that I would design. Feel free to work with neighbors on this too, if that would help.
You know how many transitions it's supposed to be?
Third,
You know how many transitions it's supposed to be?
quite a few. Enough to fill up the next slide.
There an issue with using blanks,
With using what?
blanks,
Blank.
that affects some lives, is it because you're like?
Yes,
modifying-
because you don't know when, if you're moving past, it's not bad if you're doing it at the ends. Like turn an A into a blank, turn a B into a blank, and then when you go back and forth, you're making the string smaller and smaller as you do it, that will be okay. But if you're doing a left to left and you turn an A into a blank and a B into a blank, then there's no way to know when you hit blanks if there's anything out past those blanks or not, right? Anyone think they have it? One,
I'm almost there.
bit more time. How are we doing? Anyone still working in one more time? Totally fine. Alright, let's go over an answer. All right, here is my first method. Converting an A into an X, moving right until we see a B, converting that into a Y. We need some states for that. The first state is going to be starting in Q0. When we see that A, converting it into an X, we need to be in a new state that says we have converted an A into an X. When we're in that state, when we see an A, it's different from what we want to do in the first state when we see an A. We don't want to override it with an X, so we need to be in a different state to be able to differentiate those processes. We then move right for every A that we see in state Q1. That's all we're doing until we see our first either Y or B. When we see either our first Y or B, if we see a Y, we want to continue moving until we see that B. If we see a B, then we are done and we can convert it into a Y. We then go into state Q2, which is going to be the next state after we do that, and we're ready to move back. Once we've done that, we can write the transitions for returning to the leftmost A. We move back left over all the Y's, back left over all of the A's until we see our first X. We know that that X had to have been because we started in state Q0 where we write an X. So we know there's at least one X for us to go back and see. When we do see that, we recognize it, we move right, and we transition back to Q0. That's one that's frequently missed here, is that you make a new state for that. But it turns out that we've now accomplished a loop. This is all of the transitions needed to define the basic loop of converting an A into an X, a B into a Y, and resetting ourselves so that we're back in the initial position. So we can just loop this process from Q0 back to Q0, mapping an A to a B, 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 until something happens. When we move right from Q0, and we go back and we don't see that A, we see an X. If we're in Q0 and we see a Y, that tells us that we've reached the end of the A's. So then we switch to a new state, Q3, that is going to validate and terminate. So we move now, everything that's left to the right of the marker at this point should be Y's. We're going to move right past all of those Y's. And if we see a blank, that means that we mapped all of the B's and turned them into Y's. So if we see a blank, then we move to an accepting state, Q4, and terminate. So we accept. If we see something other than a blank or a Y, like a B, that says that this wasn't in the form that we intended. And so when we halt in a non-accepting state, like Q3, and reject. So it's not that many transitions, but it is certainly a bit tricky to come up with the associated states. And the fact that we reset our state to Q0 when we finish that loop. I think that makes it a lot easier to visualize and see. Are there questions on this? Is this similar to what you came up with?
The only thing that I had different was in the group 2.
Mm-hmm.
I had to go to state 3 and then and for my validation, I was like, if it's an A, then you just continue back to where Q1 state is.
Gotcha.
And then if it's a Y, then you just continue with the Q3 setup.
That should work. Yeah, as usual with these, there are many correct programs. Some of them will have fewer states than others, some of them will have fewer transitions than others, but what's most important at this stage is the logic. If you can construct the logic for it to work, that is good. How do we feel about a slightly more complicated example? A lot of blank stares. Does this feel like something that you could do on a homework and with some practice, maybe be able to do on an exam? All right. If I don't get feedback from you, I'm going to assume it's okay, either that or You don't want to give me feedback. I need to know something like this doesn't make sense, which is completely okay. It's just that I don't know. Yeah, little bit more practice. A lot more practice. Maybe we can walk through exactly how this works on the tape. So let's come up with an example here. So let's give an example of something that's actually in the language. So we start with the A, B, and we can see how this wouldn't necessarily work otherwise. So the read-write head starts pointing at the leftmost character, this A, and we start in state Q0. So the only transition we can take starting in Q0 on an A is this one. So Q0 on an A, we're going to transition to state Q1, replacing that A with an X. So we're going to say that this is in state Q1, replace this A with an X, and move the read-write head to there. So that's what happens after that first transition. Does it make sense with at least that far with regards to reading the transition, how the transitions work and how they happen? Once we're in state Q1 and read an A, again, if this is deterministic, which every Turing machine that we've seen so far is, there should only be one tuple for handling that. Q1 on an A, there's no other Q1 on an A anywhere else here, so we have to be looking at this transition. This says stay in state Q1 and move right, replacing that A with an A. So now we just move here. And the tuple again is Q1 on an A. So we're going to be here. We're going to keep that an A and we're going to move right. So we are looking at that B, Q1 on a B. Again, there's only one such Q1 on a B transition here because it's deterministic. So that tells us to replace the B with a Y and to move left. So this B gets replaced with a Y. And this moves back left to there. But now we're in state Q2, not Q1. So Q2 on an A is telling us to move back left over all of the A's. So we're going to continue to do that. We move left to here, see another A, to Q2 on an A, we move back to here. And then we have Q2 on an X. And this tells us to move back to Q0, write that X staying as an X, and move back right. The idea is we're back on an A and back in Q0. So we've completed the first loop of this program where we took the first A, turned it into an X, the first B, turned it into a Y, and we're back on the leftmost A again, ready to do that process again. So Q0 on an A replaces that A with an X, moves into state Q1, moves right past the A, moves right past the Y, which is necessary because we want to get to the first B to convert it into a Y. So we do that, move all the way over here. And once we get here, Q1 on a B says, turn that into a Y, move back left. And we see that from Q2, we move left past all the Ys and all the As. So while we're in state Q2, we move left, 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 left until we see our first X. Once we see an X, we move back to Q0 and move right. Getting messy. Now we've completed our second loop. So we're on the leftmost A, back in Q0, replace it with an X. Move all the way right until we see this B, replace it with a Y. Move all the way back left until we see our first X. And then we're in Q0. And we've moved right from that first X. So when we do this, we are here. in Q0 at that spot. Does that make sense so far? Anything I can further explain? Q0 on a Y, we kind of have left our loop here, our loop of group 1 to group 2 to group 1 to group 2, and we're now in the validation and termination method. We're going to check whether this works. So Q0 on a Y, we need to validate that there's nothing else past the end out here. So Q0 on a Y becomes Q3, replace it with a Y and move right. So we move out here, transition to Q3. Q3 says continue to move past all of the Ys, so it will continue to all the way out past the last one, which is going to have a blank in it. And then Q3 on a blank says move to Q4. And this doesn't matter if it's right or left or anything else, but this Q4 now is an accepting state. So when we are in Q4, we know that we can terminate and accept and say that this was in the form A to the N, B to the N when we started. Good question? Do we see how this would not work if there were more A's than B's? When we moved right from here, if there was an extra A, we would be back in Q0. We would convert that into an X, and we would move, and we would never see a B out here. Q1 on a Y continues to move right, but there's no transition defined for Q1 on a blank. We have to see a B at that point. So if there were Q1 and blank, we would immediately halt and reject, and that would be the necessary state if there were more A's than B's. Similarly, if there were more B's than A's, when we're in state Q3 down here, then we would be moving past the Y's, and there's no definition for Q3 on a B. So we would immediately halt and reject because it's not in that form. And in fact, the only way to reach state Q4 at all is if there were the same number of A's and B's and in that order. There's no way to get there any other way. How are we feeling after kind of going over an example and seeing that play out? Does that help? Have we gone from here to here or here to here somewhere? How are we doing? A little bit more example will probably help, I think. But yeah, let's talk about this example in a little bit more detail. I think we've kind of reached as good as we can do for the moment. Yeah. We've kind of already done this, but here becomes the sequence of instantaneous descriptions that we can use to be able to go show what happens on AABB. So I went through it with AAABBB, but you can, as always, use instantaneous descriptions to talk about what a path through that on a particular string looks like. Any questions or confusions before moving on? This is a big challenge. I find that people who like assembly really like Turing machines, and people who loathe assembly really loathe Turing machines because it's a very similar style of abstraction and complexity. It's very low-level logic that if you like thinking that way, you like thinking that way. And if you don't like thinking that way, there's no future for you in embedded systems. But there is a great future for you in high-level coding and design. So now the question that I would have for you is, can we modify the Turing machine that we just had to represent A to the N, B to the N, C to the N? First of all, was this language context-free? It was not. It was one of the examples that we used in the context-free pumping lemma. So it's not context-free. If we can modify the Turing machine to recognize this, this would be an example of a language that a Turing machine could recognize that our NPDAs could not? That would be intriguing. So let's spend the last few minutes of class seeing if you can go from the example that we just had and extend it if we throw some C to the ends at the end.
How many states were in the first one?
I had between 0 and 4, so 5 total states.
This would be probably 2 to the 3 plus 1 6, then, right?
I actually don't think we need quite that many. We'll need a second one, so we need to differentiate what happens when we see a B from the first state, which is converted into a Y. And when we see a B in the second state, we want to move right past it, so we need 2 states to move right. Then when we recognize our first C, we can transition into a third state to move backwards. But I don't think we need a separate state because we want to move past every single B and Y and A. So I don't think we need any more state. We need a single state for that entire left process.
If we've already read the A's and the B's, why we would need to go all the way back? Why not just go back to the beginning of the B's?
Interesting. Well, in that case, there'd be no way to tell if the number of C's were different because we wouldn't be storing. We need to, as we turn an A into an X and a B into a Y, we would need to turn a C into a Z or something of the sort as we go do that.
Right, that's what I.
Yeah, so you can't go through the entire A's to X's, B's to Y's, and then move to the C's, if that was what you were suggesting. You're saying that we do one then the other. Let's go with that.
Misunderstanding what you were saying, because it sounded like you were saying after you get to through the A's and the B's processing those, so when you get to the C's, it sounded like you were saying rather than going back to the beginning of the tape, I was saying why not just go back to the beginning of the B's
Interesting.
and then use the length of the B, since you already know that the A's and B's are assumed to be.
Okay, so you could say turn the next C into and move backwards, kind of handling 2 at a time rather than 1 at a time. Sure. That would be possible to do. So if we're in state 0, we would have state 0 to convert this into an X. We would need to immediately move to state 1 to move past all of the A's to the first B, which we would convert into a Y. But then we need to convert into a new state, state 2, in order to move past and see the first C, which becomes a Z, which I would say is state 3. And in state 3, whenever we see a B or a Y or an A, we'll move left. So we should be able to move all the way back to seeing this X, which we would then reset to 0 from there. So I think our loop, instead of being 3 states, is just 4 states. Then when we validate and terminate, we just need to make sure that from this new state 4, once we're back over all of this, we would be at the end of this set of X's. So we would have gone back at the end and be resetting to here. So we want to make sure that we have no transition defined in state 4 for a B. So we should be going past Y's and Z's. and going and seeing a blank. When we do, turn that into state 5, which we accept. So to me, this is a 6-stater. Although it's possible as well that this 2 could reuse the 0. No, you can't. You want to distinguish it here. So kind of the same form, not too much more complicated. Do we have a solution? Anyone have a full solution for us? Almost there or there?
I'm there.
Nice.
You need to add one on state 2.
Yes, there should be a Z transition for state 2, just in case we go out all the way past some Z's until we see our first C. My recommendation for people who are struggling with this, try to finish this off at home. But the conclusion from this is that, yes, this is very possible. And because it is possible, we can show that Turing machines are more powerful than the last class of languages that we discussed. They're more powerful than context-free grammars. They're more powerful than any form of pushdown automata. And in fact, we can use math that I won't go into to show that, of course, we could write any program from any programming language, and we can simulate that with a Turing machine. They're equally powerful. Because we can write directly to the tape, we can now produce output in addition to using them as acceptors. So any program that you could write that has any kind of output whatsoever could be simulated by a Turing machine. Now, granted, I don't know why anyone would ever want to do that. Actually use a Turing machine for that purpose. But that said, it is the most computationally simple system that has that level of power that we have discovered. It is incredibly simple to get that level of power. The program's disgusting in complexity, but the actual power of the system itself, we can only move left or right, read and write from single cells. It's amazing that that is capable of everything that we could do with a computer. So yeah, an algorithm just transforms input into output, and a Turing machine we can show is capable of doing exactly that. Taking any input on the tape and converting that into any output that we could want. So it is an algorithm simulator. We're going to come back tomorrow and get some more practice. How do we feel? Like it's Monday?
It is Monday.
It is Monday. It feels like Monday. All right, I have office hours starting in an hour. If anyone has any questions on the current homework, anything we're going over in class, or the CYK project, or the upcoming exam. So I will see you for that, potentially. If not, I'll see you tomorrow. Take care.
You know that you can prove